Okay. All right. Now, we're to ion cyclotron waves. Now, why did I get confused? Because I was assuming that the electron contribution to the polarization, namely this, was the more important term than this, because electrons usually contribute much more to polarization than ions. And then I was assuming that we needed affirmative action for the ions to make this term equal to this term, and therefore omega should be very close to omega I. Now that's the right idea for ion cyclotron waves. That's how they work. But I only left out one little thing. The problem was that this term was actually smaller than this term because omega E squared at the bottom is more small, is larger by a larger factor than of the mass ratio and then the numerator. So this actually ended up being smaller than this one. Now physically, why is that true? How did the electrons get shut off? They got shut off because I was considering motion exactly perpendicular to the magnetic field. And electrons, the motion that's perpendicular to the magnetic field is more easily done by ions than electrons. In other words, when you're exactly perpendicular to the magnetic field, you're working on drift, and ions drift better than electrons, which is why this term is bigger than this term. But if you're not going exactly perpendicular to the field, then you tell me, then what? Then electrons generally will be accelerated faster than ions. Let's take the unit vectors of k and b. Suppose it's equal to or greater than m sub e over m sub I square root, which is a small number. It's the square root of 1836. It's about 43. So k dot b can be nearly perpendicular, but off by 1/43 of a radian, which is like 1.5 degrees. Then, when the electrons feel an electric field, along the k vector, let's say this is the k vector and this is the field, then they can actually slide along the field with let's say x double dot for the electron is equal to E over m sub e times the cosine of k dot b, the cosine of the angle. So that's equivalent to saying that so if this criterion holds, then once again this will be greater than than the ion acceleration. In other words, even though they're capturing only a little bit of the electric field, they're still accelerating more rapidly than the ions. So, therefore, the electron term dominates therefore the electron, let's say it's much greater than. Therefore, the electron term dominates the ion term. And if they're both, then the argument I said before works. If these are much greater than 1, in other words, I have quasi-neutrality, then omega has to be very close to omega I, so this term balances this term. No, it has to be very close to omega I. Because this term is bigger than this term now, because there's a finite angle, and the electron polarization is this term. And to make this term as big as this term, I have to make the denominator and the ion term small. So it's electrostatic waves that are being restored by the ions, except that the electrons are drifting with the ions to make quasi-neutrality. But the wave motion is led by the ions, and the electrons drift along with them. Anyway, it's kind of like the electron cyclotron frequency. It's like electron cyclotron waves in the upper hybrid mode for when there's very small plasma frequency. What was the upper hybrid mode when there was very small plasma frequency? It was, then this term dominates this term. It's just omega E. It's just electrons gyrating like this, so that when they're here, there's a charge density enhancement, and then when they're here, it's depleted, and they go like this because I set up the initial conditions that way. It's just the phases of individual. Yeah. Now here the ions are doing this, and the reason the electrons, and the reason that the ion plasma frequency is not entering the oscillation is that the electrons are exactly balancing out the electrostatic contribution of the ions. So it's just the magnetic field that restores the density, the density variation, and not the electrostatic separation, because the electrons are following it. So there's quasi-neutral. You don't get any electrostatic effects. You just get the magnetic effects. Question? Okay, well, I'm glad we got that straight. And it turns out what I said was right. I just forgot to say that the electron polarization, as I wrote it here, is not the correct expression when you have a slight obliquity between the K vector and the magnetic field. And by the way, that applies to shock waves too. The nature of the shock wave changes when the angle between the shock vector and the magnetic field vector is exactly perpendicular or perpendicular to within 1.5 degrees. 1 1/3 degrees. If it's exactly perpendicular, the electrons can't short out the fields along the electrostatic fields along the shock, and you can get. And I guess you can get strong electric fields across the shock, which can basically it's an ion electrostatic shock. The electric fields can shock the ions and interrupt their motion. But if you have an oblique shock, the electrons can move along the field lines and they can short out any electric fields that the ions that would otherwise stop the ions. Remember, if you wanted to have an electrostatic shock wave, you have ions flowing into a shock. Well, we haven't discussed shocks yet, have we? So never mind for now. But when we do, we'll see that in the collisionless shock, you need electric fields to, or some kind of electromagnetic field to scramble the motion of the ions that are flowing in and convert it to heat. And the question is, what is that electromagnetic field? Is it a magnetic field, or is it a pure electrostatic field? And sometimes you can have electrostatic shocks, but it's not easy, because if you have an electric field that's strong enough to stop ions, then it's so strong many times over to stop electrons that why shouldn't the electrons short it out? So that's why collisionless shock waves is a hard problem, and a lot of people say it's still unsolved because we don't yet know how they work. Okay, now it's 3:15. Maybe I can say some qualitative points about warm plasmas. Warm plasmas, in some sense, are like cold plasmas. Except that in calculating the response of the electrons, I have to include the Doppler shift of the frequency as seen by that given electron. Now the Doppler shifted frequency is omega minus k dot b. If an electron is moving in the direction of the wave, if it was moving exactly at the speed of the wave, then the denominator would be 0. And there would be no oscillatory cancellation. That's always seeing, and that's where the trouble comes, when this denominator goes to 0. Otherwise, instead of just doing this for a cold plasma, I would just do integrate over velocity. Let's say it's a thermal distribution. I integrate over the thermal velocity. And instead of omega squared, I just have the Doppler shifted. The problem is that when this goes to 0, life gets very confusing. Unless you really know what's going on. And the first person who tried to solve the Vlasov equation self-consistently was Vlasov. And he didn't know what to do with this denominator. The Vlasov equation is just the equation in phase space for the. It's like the Boltzmann equation, but instead of having a collision operator, you have acceleration due to electromagnetic fields. And that has a df/dv term in it times acceleration. Just like the Boltzmann equation has a v dot df/dx term, which is convection. Acceleration is really convection in velocity space, and we'll get to the Vlasov equation soon enough. But the point is that Vlasov didn't know what to do with this denominator, so he just integrated over every place except where it went to zero. And
It couldn't do.
and he got the right dispersion relation except for the Landau damping. Landau was the second person who tried to solve the Vlasov equation. He did it right, and he found that the resonance it did just what you expect it to do. It's like any other resonance. It puts energy in or takes energy out of the particle depending on phase relation of the particle with the wave.
But this is a mathematical problem. Couldn't he solve it by adding some imaginary part and with poles and something?
That's how.
Exactly how we did.
No. Well,
I epsilon and.
That's easy
No.
for you to say, but the
Why?
point is you have to choose a contour of integration. Do you go above the pole or below the pole?
You have to choose the contour such a way that on this semi-arc it should, when you take it to infinity,
Yeah.
it should cancel out. Can we do it here?
What you
Go
can
to-
what should cancel out?
The function itself on this contour. When you take
I'm doing a contour integral. If I go above the pole,
yes.
then there's no pole in the contour, and the answer is zero.
It should be the Cauchy integral.
But you could go above the
way
pole.
to do it is when you take, I think that you're talking about infinity, but when you're going close to the pole, you go above it or below.
And how do you choose? Do you
Do
go
you
above
include
it
it
or
or
below
not?
it?
You should include it. You
No,
should
what is
take-
included? Don't use the word include. I said the question
This
is do you
pole-
go above it or below it in frequency space? I can make it plus I epsilon or I can make minus I epsilon.
So you draw a picture, it will be much easier.
Okay, let's say this is the omega axis. Or actually let's say it's the V axis.
Yeah.
The axis of integration, and this is omega over k. I'm integrating over velocity. I hit the pole. Do I go like this and forward, or do I go like this and forward?
No, I
think remember
meant.
you went below it. I just don't know why.
I don't even remember. I just remember the reason. Anyway, Vlasov guessed, and he guessed wrong.
Okay.
He basically took us the sum. He couldn't figure out which way to go, so he said, "Look, I'll take the sum of the two and take the average of the two. I'll go above it. I'll go below." His reasoning was probably, "Look, if omega is real, this imaginary stuff has no physical meaning, so I'll just take the average of the two, so the imaginary term cancels out." And that's perfectly reasonable thing to do because you get what's called the principal value of the integral, and that includes all of the non-resonant contributions to the polarization tensor. And that's what you have for a cold plasma. This is for finite omega. You never have any resonant particles, and you get this for epsilon. Here, if you let's say there are very few particles at velocity equals omega over k, then I would just do a Taylor expansion of the denominator and the numerator, and I'd get the cold plasma contribution, and the next term would be k squared v squared over omega squared, which is just sorry, and this is the if f is a Gaussian, then this is the thermal average. Looks like I don't know what ID stands for, but it's the thermal velocity. It's the average of this. Obviously, should be a small k.
What
No, a small. This should be a small f, like this one. This is basically just the average thermal velocity. So this is just a term proportional to thermal velocity squared, which is the sound velocity due to the electrons. And the m, the electron rest mass that appeared in the plasma frequency, and I multiplied it by it was multiplied out here, but when I Alright, let's follow this. Boltzmann's constant. Anyway, the point is, it's the thermal velocity squared over, and it's affecting the phase velocity, because if the plasma frequency was 0, let's say, then this would just be, then I would get the omega over k. You know what, let's say in the special case where omega p is 0, and what we used to call an electrostatic mode is now just a longitudinal mode, and it's 1 is equal to 3k squared over omega squared b thermal squared. And what is omega over k? Omega over k is the sound velocity. Anyway, it's just a sound wave. It's sound wave is the square root of 3 or something times the thermal velocity of the electrons. So it's actually, you can think of it as being a collisionless sound wave, I guess.
Can I ask a question?
Yeah.
I forgot how you get the minus omega minus k.
Omega minus what?
The omega minus k part. In the
I'm expanding the
no,
denominator.
this one. If you can go this one. How do you get this equation?
I substituted the Doppler frequency for this frequency. I just substituted
Why is it
Omega-
integral over f?
because I'm integrating over all the particles. They all have different velocities. Okay, what happens when f of v is finite where omega equals k dot b? Raises the issue of resonance. Now, usually when I teach the course, I assign this as a homework problem. Solve this equation. And you see that when omega happens to equal omega 0, you get a resonant behavior. Everybody should learn that in second year.
Now you have
Physics.
2 poles, so you
What?
don't so you don't have problem of going above or below. You just split poles.
I didn't say it was a problem anyway. I just said Vlasov it was a problem for Vlasov. But the question is, if you're going to answer the question, of what contour to take, you have to understand what the physics is. Otherwise, you're just guessing. That's the moral of the story.
And here the inorganic parts solve the mixing. Right, and the omega equals omega part.
Can't hear you.
No, what I remember about this equation is that a lot of people forget the inhomogeneous part, which is when omega is equal to omega. I don't know,
No.
it's when it's cosinus. When you have e to multiply by cosinus omega t. Never mind.
It's true that you have to keep the initial conditions in mind. Now you can assume that things started from minus infinity, but then that's true only if the initial conditions were that everything was 0 at minus infinity. Because any term proportional to e to the I omega t, actually that is the main point here, is what are the initial conditions. If you throw them away, if you say they're 0, and at some point they became non-zero, and if you also look for e to the I omega t time dependence, what's the only way to do that? The only way to have 0 at minus infinity when you have e to the I omega t, or e to the minus I omega t, is to give omega a slight imaginary part, so that you can forget about the initial conditions at minus infinity. And that's how you pick the contour, is that you give omega the correct imaginary parts so that the initial conditions at minus infinity go to 0. Now that's not necessarily true for real plasmas. If you suddenly switch on the field, it's not fair to use that time dependence. Then you have to take into account the initial conditions. But then you have to solve the equation more correctly. You have to use Laplace transforms, which you can do for arbitrary initial conditions. So that's what Landau did. He solved the Vlasov equation using Laplace transform, keeping account initial conditions. I don't generally do it in this course. Go through his calculation because I've a morbid fear of Laplace transforms. But basically, for resonant particles, if you start without any initial conditions, then when you finally get activity in particles, the resonant particles will be 90 degrees out of phase with the electric field, with the force, which means that the velocity will be in phase with the force at all times. And whether it's in phase so that it absorbs energy, or in phase so that it releases energy into the wave, is a question we still have to get to. But the point is that it's in phase with the wave. Yeah. Now, it looks like I do this every which way except Laplace transforms. Try to give a physical explanation. I guess we might as well follow the notes here. If you solve this equation with e to the minus I omega t dependence, you get this solution very easily. I'm sure you've all done this as undergraduates. No?
This, yeah, with poles.
What?
The contour integrals.
No, it's not contour integrals. It's just inserting this dependence into here and solving.
Yeah, I think we do that.
You should do it in physics 3. The point is, when you have a damping term, this is the damping term, B, you get an imaginary part. Otherwise, you would get a 0 in the denominator. And depending on the sign of this, of B, you'll know if you go along the real axis of omega, you'll know whether you're going under or over the pole.
In physics 3, in our exam, we had a question just like this.
Yeah.
So everybody spent like an hour trying to divide the amplitude and the phase.
Trying to what?
To separate the amplitude from the phase. So it was very funny. I mean, you take this, you find the amplitude, and then you divide.
So writing the whole thing in the form
it was
of
a long
H times e to the power I theta.
Yeah, it was very long.
Oh, okay.
Yeah.
So you find that phase shifts from 0 to pi, and when it's just under the pole, it's around 90 degrees. Now, when the denominator is at a minimum, you see that x is 90 degrees out of phase because it's the denominator is purely imaginary.
Again, when omega is what?
When omega is equal to omega naught, which is the real part of the natural frequency of the oscillator, then the denominator is purely imaginary, and that means that x is 90 degrees out of phase with the electric field, which is in the numerator. Otherwise, x is either proportional to e with a real constant of proportionality. It could be the positive or negative depending on whether omega is bigger or smaller than omega naught. Omega naught. Okay, now B, note that B has B has the same x dot has the same dimensions of x double dot, which means B has dimensions 1 over time. And what's the physical interpretation for B? It's the it's the lifetime of a natural oscillation in the presence of damping.
It's the width of the Lorentz.
Yeah. But what does that width mean? It's really the amount of time that it takes to fall out of phase, at which point you're no longer resonant, because after you've fallen out of phase, the oscillations will subtract energy out rather than give energy, and that's considered a non-resonant particle. Note that the total energy absorption does not depend on B, because the smaller B is, the narrower the resonance and the fewer particles last. On the other hand, the time that they last is proportional to 1 over B. So you have, if B is multiplied by 2, you have half as many particles, twice as many particles, but lasting half as long in the coherent electric field. Hello? Okay, thanks. Okay, so that's an important point, is that I can invent a B when I need it, because its value doesn't really affect how much energy gets absorbed. I can, whenever I get to a denominator that has a resonant singularity, I can just invent an I epsilon, because the value of epsilon doesn't really matter too much in most situations.
This is what London did.
Yeah, except that he used Laplace transforms to do it really rigorously. Okay, so here's where I discuss the inhomogeneous part. Right?
Yeah.
True solution. Well, A and B are called the homogeneous or the inhomogeneous part? I can't remember.
It's a different question.
What?
Yeah, it's a different question. You have E multiplied by E minus yeah, that's fine. This is different. This is different. We have a different question. I don't see a dumping part.
Well, I didn't put one in yet.
Then you're right.
The point is that these homogeneous, is this called the homogeneous part or the inhomogeneous part? What?
This is homogeneous part.
This is the homogeneous part. And why is it called homogeneous and this is inhomogeneous?
Because if you put in homogeneous part, you get in your equation 0 בסוף, אתה מקבל 0. if you have some different.
Why is it, no, the question is why is it called homogeneous? What's homogeneous about
This
it?
is solution of differential equation with differential operator acting on y on some variable equal to 0.
That's
Because
I've never understood why it's called homogeneous, and that's why I never remember. You can turn if your door's closed. You can turn the air conditioning.
it looks like you can translate everything in x in the independent variable and you still have the same differential equation.
Maybe because when you don't have initial conditions, then you have a whole family of solutions.
Because you only have dx terms, so you can translate in x.
Never. Yeah, if E is a function of x, then that makes it inhomogeneous.
Yeah.
Thank you. Maybe now it'll stick.
Again, if
Alright, now if
but if it's a constant,
Then
it's not homogeneous. But if it's a constant,
the constant is not homogeneous. It must be equal to 0. Differential equation is equal to 0.
and if it's a function of x, it's still not homogeneous.
It's still homogeneous. It must be 0.
Yeah.
Alright, now if I added a small damping term, these homogeneous terms would damp out after a finite time, and I'd be justified in ignoring them. And that's what I meant when I say if I put in damping, I can neglect initial conditions. If I put in damping into this equation, where is it?
Yeah, this one.
Well, never mind. It was written above.
Yeah, this one.
To this one, yeah. Transit solutions. Instead of having just being proportional to omega naught, they're now proportional to. I think I meant to say omega naught here. In other words, I can either pull omega naught off the real axis. I can either pull omega naught off the real axis by giving it a small imaginary part, or I can give omega a small positive imaginary part and just say that the initial conditions went to 0 at minus infinity. But either way, I'm picking the imaginary part so as to make the homogeneous part of the solution vanish at the time of interest. Okay. Now the question is, if I have a Langmuir wave, an electrostatic wave, so the electric field changes in direction, but it's moving. It changes with space, but it's moving in a given direction. Take a single wave, and the resonant particles are the ones that are moving in that direction. V equals omega over k. Minus omega over k isn't resonant. So for the resonant particles, some of them are going to feel a potential gradient that's pushing them ahead, and some of them are going to feel a potential gradient that's pushing them back. And it kind of looks like there's going to be half and half, because the wave has equal numbers of equal. The net potential change in the plasma wave is 0. Now, over some time average, is there a net transfer of energy from waves to particles? Well, arguably you could say no, because let's say the particles are initially homogeneously distributed, and the wave is symmetric, going, for those electric fields pointing in one direction as in the opposite direction. So I should have as many particles gaining energy as losing energy. I think this repeats what I said before. Okay, at this point, you can either do what Landau did, or you can do it the way I prefer doing it, because it's a lot easier, which is to just solve the equation, to see what solves the equation, and it's basically algebra. Now, I don't seem to have used the Vlasov equation here. But here it is. This is the Vlasov equation. And if I assume e to the ikx minus omega t dependence in one dimension, then this is the acceleration, and it should be df dv, right? So what's the acceleration? The acceleration is E times the electric field, and it should be E over m. E over m. So the Vlasov equation becomes this. There's so many big F's here, I'm not going to try to change it. But it's still the same phase space function.
F1 is not smaller than F0.
Yeah, what I assume is now, first of all, E is going to have this dependence, but F is going to be the sum of two terms. F naught is a spatially homogeneous. It's just a constant, and it tells you it's a constant of space and time. It tells you just what the state of the particles was before the wave started growing at minus infinity, and F1 is a function of space and time.
See that F0 is function of the velocity. All of them are the function of velocity.
Right. So I can write F naught as a function of velocity. F1 is a function of velocity, space, and time. Now, now if I just insert this and this into this equation and this into the Vlasov equation, which was up here, I get this. I should say one more thing. I'm solving it perturbatively, which means when I have a first order term, which is, v is not a first order term. That's just an independent variable. But a is proportional to e, which is a first order term. So, because this is a first order term, I'm just keeping the zero order term of this, and that's why I'm assuming this term is a times df naught dv, and that's why there's a df naught dv here. And now this is just very easy to solve for f1. It's equal to this. And here you see the prospects for a resonant denominator. Now, the next thing I want to do is find the self-consistent solution to Vlasov equation plus Maxwell's equation. Now, since this is an electrostatic wave, the only Maxwell's equation that's important is Poisson's equation. So we've gotten up to here so far. Now, at some point, this so far is okay, but at some point we're going to have to do an integral.
What?
So,
I have a question, to the general question. Can you get back to the Vlasov equations?
yes.
No, go down.
I have a problem of understanding. This is a differential equation, and those variables, they are dependent on each other, right?
Then on what?
On each other.
No.
V is dependent on x.
No.
No?
V is an independent variable. This is an equation for phase space.
Ah, okay.
And these are totally. It's not like fluid mechanics, which is what you do. This is totally Eulerian coordinates.
Okay.
You're not moving with the particle.
Okay.
So it's a given V, and you're watching how F changes at that V.
But you still have dx dt and c.
Wait, dx dt is v?
Yeah.
So they're dependent.
No, don't listen to him.
But you do, because you get that v from dx dt, and this a from dv dt.
So this is
Yeah, that may be, but
after
V
you
and
make
X
this
are
change-
independent variables.
Yeah, but after you make this change, you.
I didn't make any
Wait,
change.
wait,
I
no.
didn't make any change.
I'm confused.
I know, because you're listening to him. Don't listen to him. X is an independent variable in phase space. V is an independent variable
Okay.
in phase space. It's
okay.
like momentum.
Okay. Now it's okay.
It's just that when particles that are point X comma V, emphasis on the comma here, the interpretation is that those are the particles that are moving in the direction of V, and therefore their change is given. It's like a Boltzmann equation. At a given V, and this is X, if F is like this, and they're moving this way, then df dt is going to be negative, because df dx
Yeah.
is positive. So all this is still phase space. Now, at this point, we solved for F1, but we haven't solved for anything else. We haven't solved for E1. We've just assumed it has either the ikx minus omega t dependence. But if it turns out that we can find an omega for any given k, that'll be great. But we still haven't found it yet. So how do we find it? Well, so far, I'm just discussing the response of a plasma to any given wave. As far as the plasma knows, this is a perfectly good solution because it doesn't care what omega is, it just feels it. And it doesn't care how it was made. But I, the plasma physicist, want to know, how does the wave make itself? What does the wave do on its own when I'm not there to provide the wave? In that case, the plasma doesn't merely have to solve the Vlasov equation, which is basically Newton's equation. It also has to solve Maxwell's equation, which means it has to solve 4 pi rho is equal to grad to the divergence of E. Now what is rho? Rho is equal to rho 1 because the net charge in the unperturbed plasma was 0. And this is equal to E n1, and this is equal to E times n
N0?
Okay, now let's just make
Without the N outside.
let's just make n1 explicitly a function of x and t. Well, and v of course. But rho, no, n is not a function of v. Yeah. And rho is just a function of x and t.
It's without the N outside, no? Because integral f d3v is N.
What?
What is the N within the outside of the integral?
This is the 0.
It's not a good sign because N0 is 0.
No,
It's confusing.
n0 is not 0. But I'm normal. You know, I can say
You're
that
right,
the
you're right. You're correct. Yeah.
I can say that the integral of f of v x t
This is N.
is equal to n0. But I can also say that it's usually what people do is they say it's equal to 1 and they put the n0 outside. So this is normalized to 1. Now that's not quite the way I did it up there, so actually let me do it the less fashionable way and just say this is n0. Now I substitute f1 into here, make this parenthetic, and I say rho is equal to E times E over M. That was this.
Multiplied by IK.
Well, I mean, this here I can already say that this is IK dot E for an electrostatic wave. Okay. So now I have this E and I have this F1, but so let's take this E over here and this E, big E over M over here. And now we want to integrate the F naught dV oh, it's 405. Anyway, this is, I have to set this equal to IK dot E. And notice the E cancels. And now I have an equation which fixes omega. This is just given K, this is an equation that fixes omega. You're also given dF naught dV. Everything is fixed except omega, and that tells you what omega has to be. And when you solve for what omega is, if you do it correctly, you'll get an imaginary term. That's the point. Because you'll have to include the I epsilon in that integral. Oh, mercy. Do you want to... Does that... I think Arka needs the computer to... Do you want to wait till tomorrow?
I asked him, he told me you can keep it.
Okay. Stop.